Metalworking fluids are widely used in metalworking industries for machine cooling and lubrication during different metal finishing processes, because of their good thermal conductivity and lubrication properties. Most metalworking fluids are oil and water emulsions with oil concentration in the range 1% to 10%. In addition, metalworking fluids contain also additives, such as antimicrobial compounds, corrosion inhibitors, emulsifiers, pressure additives and anti-foam agents. In practical working environment, oil concentration changes from day to day due to water evaporation, bacterial attack and oil adhesion to metal parts. However, maintaining the proper oil concentration is necessary to prevent potential tool malfunctions and reliability problems. The official technique to measure oil concentration in metalworking fluid samples is manual titration with hydrochloric acid. This reference method is accurate and not affected by fluid contamination, but needs to be performed by trained personnel in a laboratory environment, hence is not suitable for in-situ measurements in industrial plants. The industrial standard for oil concentration measurements in metalworking fluids is refractometry. The refractometer is a cheap instrument that can be used also in production environments. However, it has also some important drawbacks, since it needs to be calibrated frequently, its accuracy is affected by fluid contamination and samples with certain composition do not provide clear readings, even if not contaminated. A novel instrument is here presented to measure the oil concentration in metalworking fluids. The instrument estimates the oil concentration measuring the sample viscosity. The fluid viscosity is measured using the falling ball principle. An high-precision chrome steel ball is allowed to fall under its gravity in the instrument between two fixed points and the time needed to cover such distance is measured. The time required for the ball to fall between the top and bottom target points is measured by means of two inductive proximity sensors, detecting the presence of an electrical conductive body at the near distance of about 2 mm. The instrument performs the oil concentration measurement at environmental temperature and compensate for viscosity variations due to temperature using a PT100 thermistor. The lack of a controlled heating system results in reduced power consumption as required for a battery-operated system. The instrument is battery-operated and suitable for in-situ measurements in metalworking plants. The proposed instrument features an electronic board, based on the microcontroller STM32 by ST Microelectronics. Its power supply is provided by four 1.5-volt alkaline batteries. The system features 4 buttons for user interaction and a liquid crystal display with 2 lines of 8 characters each to display measures data. The power consumption is low. The average current drawn is 28 mA if the display backlight is turned off. A non-volatile EEPROM memory is present on the designed electronic board to allow the user to store the calibration parameters for better accuracy in the measurement of oil concentration. The physics behind the falling ball method for viscosity measurement is here presented. A ball moving in a fluid under its gravity is subjected to 3 different forces. The gravity force, acting downward, is the product of the ball mass and the gravitational acceleration. The buoyancy force, exerted by the fluid and opposing to the ball motion, can be expressed as the product of the displaced liquid mass and the gravitational acceleration. The viscosity force, also opposing to the ball motion, is proportional to the liquid viscosity and the ball velocity. Since, after a short transient, the ball moves down at a constant velocity, all the forces acting on the ball must be in equilibrium. The result is that the liquid viscosity is proportional to the product of the ball falling time with the difference between the ball density and the liquid density. At the beginning of the measure of oil concentration, the instrument is filled with the sample under test. Then, the ball is allowed to fall under its gravity inside the instrument and roll on its surface. When the ball exits from the top proximity sensor active area, the counter is activated. When the ball enters in the bottom proximity sensor active area, the counter is deactivated. The measured falling time is used to estimate the sample oil concentration. Results at a temperature of 25 Celsius show how there is a very good linear correlation between the ball falling time and the sample oil concentration. The resulting determination coefficient is 0.989. Measures have been carried out at 5 different temperatures and the results show that the ball falling time is function of both the oil concentration and the temperature. For each tested temperature, there is a very good linear correlation between the ball falling time and the sample oil concentration. For a given oil concentration, the ball falling time is function of temperature, based on the following exponential model, proposed by Reynolds in 1886. The empirical parameter, B, has been also found function of the sample oil concentration according to the following equation. The PT100 thermistor measures the sample temperature, that is used to compensate for temperature variations by means of an iterative algorithm and calculate the unknown sample oil concentration. Metalworking fluid samples prepared using different oil products are characterized by different calibration equations, due to different viscosity of the oil products. This is accounted by a calibration procedure where test samples with oil concentrations of 2%, 6% and 10% are tested and the calibration equation built on the measured ball falling times for the 3 cases. The parameters of the calibration equation are then saved in the non-volatile memory on the electronic board. And now, a short video of the instrument in action.